Yeah, this work is joined with Yu Hao from Columbia, because he's also in the audience. Yeah, and Xina from FlashFlows, Elin and Stephen from NYU. So when it comes to the DEX, I guess the most likely in the first design comes to mind is the CFM like Uniswap. And besides CFM, maybe today's keynote may further convince you that maybe batch auction is also a good idea for the DEX design. So our paper discussed optimal MEV in both scenarios, but in this talk, I will focus on the latter, namely the optimal MEV in batch auctions, because I think this topic is less noticed by the community, and I want to draw attention through this talk. Yeah. So let's just go straight to the point. So in decentralized exchanges as a DeFi application, so the people who own some amount of that X and want some amount of X token and want to exchange them for some Y token. Facing these customer needs, when we design a DEX, no matter it's CFM based or batch auction based, I think the designers should answer two questions. The first one is about where should we find the Y token where what the user needs, and secondly, suppose we have the Y token, how many should we give the user? CFM answered this question with two novel concepts. The first one is liquidity pool, that which collect the both types of token in advance from the liquidity providers and the previous orders, so that whenever someone comes to market, he can trade with the pool directly without waiting for others to match, like in the design of liquid order books. Yeah. And in this process, the exchange rate is determined by a constant function. And I guess we all believe that, we all agree that this design is very clever. It has many good properties, like it only needs very lightweight computations. But it also brings some unexpected MEV issues. For example, on the left, I show the sandwich attack. You may find that in this design, the exchange rate is not fixed. The price of a token changes immediately after a trade. So the sandwich attacker could exploit this user transaction to cause a price movement and benefit from buying low and selling high. And sorry. And in addition, the exchange rates of different DEXs, different CFMs, may be inconsistent, which means, for example, suppose there are three DEXs. The blue one is for the exchange between token X and Y. The orange one is for Y and Z, and the green one is for Z and X. So if the product of the exchange rates is greater than 1, then with some initial delta X, the arbitrager will receive more X after these cyclic exchanges. These two are very common behaviors in CFMs, but as I will show later, they are no longer a problem in the DEX based on the CF batch auctions. Yeah, so let me first remind you how batch auction works. Actually, in the batch auction, the liquidity is the transaction itself. It means that the transaction will exchange with each other, which means they will provide each other with the token they need. And specifically, a mediator will collect the transactions for a period of time. For example, all transactions after the last block. And these transactions are not limited to just between two tokens. They can, involve many types of tokens like the USDT, Ether, DAI, and many others. And after grouping these transactions in the batch, the mediator will send them to a batch auction DEX. And based on this transaction information, the DEX will calculate a price for each involved token. And with this price vector, we can answer the second question that, the second question that the exchange rate is exactly the corresponding price ratio. And for example, for the first transaction, who is gonna for USDT, for Ether, we can find their prices are 2 and 600 respectively. So the exchange rate should be 2 over 600. So as a result, the first one received by Ether. And similarly, the second one received 200 DAI, the third one received 300 USDT. But for the last one, the exchange rate between DAI and USDT is 3 over 2, right? But it's smaller, it is less than the threshold 3 here. And here the 3 means that the user requires the exchange rate should be at least 3. So this transaction will fail and the user receive its original 500 DAI. So this is the outcome of this batch exchange. So everything looks good, but the only problem is how should we set this price vector? Actually, I would say different DEX design, different batch auctions have different design at this point. And our paper follows the design of SpeedX, which connect this problem with a classic economic concept called market equilibrium. So in here, the market means the pure exchange market. And in this market, we have indivisible goods, and M traders come to market with some initial endowments. It means that M traders come to bring some items to the market and want to exchange them for some others. And each trader has her own preference over these goods, which is denoted by this UIJ. And here X is the final allocation, which means XIJ is the amount of Guji that the trader I finally received. And then in the linear market, the each trader's utility function can be represented in this linear way. And recall that in the batch auction setting, we also have n types of goods, n types of tokens, and m transactions. And for each transaction, it brings some initial token to the market, and one exchange for some others. And it also specifies a threshold, the minimal acceptable exchange rate. By translating each user transaction into a linear utility function like this, the batch auction, we can treat this batch auction as a linear market as well. So that we can borrow some solution concept from the literature of economics. And actually, these two settings face the same problem, that is how to efficiently reallocate these goods in the market, these tokens in the market. The solution was captured by a so-called solution concept called market equilibrium, which consists of a price vector P and an allocation vector X. And here, this pair, the equilibrium means that this pair P and X should satisfy 3 conditions at the same time. The first one is market clearance, which means all initial tokens, all initial goods should be reallocated. Nothing should be locked in this market. And the second one is budget constraint, which means according to this price vector, the price of your initial tokens should be equivalent to the price of the items you finally received, the finally allocated. And the last one is individual optionality. It means that given a price vector P, everyone's utility will be maximized under the allocation X. And I would say to satisfy these 3 conditions at the same time is highly non-trivial, but very likely previous work from the by the economists could imply that in our batch auction setting, there always exists a unique price vector or price equilibrium. And further, the many there is a long line of work by the computer scientists they propose several efficient algorithm to compute this market equilibrium. And beyond these theoretical results, Ramsey, Will, and Maziris extends this beautiful market equilibrium idea to the blockchain setting. They develop a more practical computation algorithm and develop this batch auction DEX called SpeedX. And our work are based on this formulation. So far, I think we have been more familiar with batch auction, and we can continue to discuss the MEV in this scenario. And yeah, so actually, it's widely believed that the batch auction is kind of MEV resistant. It's mainly because all exchange rates should be skewed, all transactions will be executed at the same, according to the uniform prices. So for example, on the left, I show an example which consists of 3 tokens XYZ and some transactions. 2 of them are both want to swap from Y to Z, and actually, on the equilibrium, these two transactions will be executed at the same exchange rate, PX or PZ, in batch auction. Also, the sandwich attacker cannot exploit the user transaction to cause some price movement, because everyone will be executed at the same price. So the sandwich attack doesn't work here. And on the right, we can see in a batch there may exist a cycle, but it's easy to verify that the product of the exchange rate will be always 1. So there is no arbitrage opportunity. So given this, we want to ask the question that, is this the end of the story? So does batch auction have totally solved the MEV problem? And actually, as I show here, our answer is no. The point is the execution outcome of the batch depends on the transactions in the batch. So intuitively, if we have the power to manipulate the batch content to change the transactions in the batch, the outcome will be different. And in this process, maybe we can make some profit, right? So here is a concrete example to show this idea. So suppose there are 3 tokens XYZ and their prices are all 1. And here the price is the price of token in the attacker's mind. Recall that there is a mediator who needs to collect the transactions and send to the batch auction. So we suppose this is the price of token in the the mediator's mind. It can be the price of token in the centralized exchange like the Binance. It's just the self-belief. And there are 3 user transactions. The first one is 2x for at least 1y, and 1y for at least 4z, and 4z for at least 2x. So we claim that if you collect these 3 transactions in a batch, then they will be executed as the figure shows. But as a mediator, if you want to make some profit, you can do like this. You just ignore the Y to Z transaction and insert it to your own attacking transactions. And I claim that if you do this by collecting them in this batch, they will be executed as well. But in this process, you will make some profit, because according to this extraneous price, the utility will be $3. And alternatively, maybe you can also just replace this Y to Z transaction with your attacking transaction but of the same content. And by doing this, your utility is also 3. So this example has told us that MEV is possible in batch auction, right? Then we ask the next question, that what's the optimal MEV strategy? How to optimally attack a batch auction to maximize our utility? Okay. To answer this question, let's first formally define this problem. Recall that MEV refers to the additional value by including, excluding, and reordering transactions. And in the batch auction setting, you may realize that the sequence doesn't matter. So we can ignore this reordering strategy. Then the strategy space becomes given a set of user transactions. You can, as a mediator, as the attacker, you can select a subset from them and insert some new attacking transactions, which forms a new batch, right? And this new batch will be delivered to the DEX, which will compute the outcome of this execution. And the outcome will determine your utility by this attack. So intuitively, the attacker brings some token to this market. according to the extraneous price, this may be worth like $50. And after the execution, you receive another bunch of tokens, which may be worth like $300. And the difference is exactly what you own, or what you benefit from this attack. Yeah, this is the definition of this utility function. And the problem is, what's the optimal strategy to maximize your utility? Okay, here are our main results, which contains two parts. The first one is, if the user transaction forms a Fisher market, then we propose an algorithm to compute the optimal strategy in polynomial time. But if they form an algebra market, the problem becomes harder. I will explain the definition of Fisher market and algebra market later. But before going into the details, I would like to show some combinatorial structures, which are very helpful for understanding what should the optimal attack look like. Given a set of transactions, we can construct a so-called economy graph as follows. So each vertex in this graph corresponds to a token. And if there exists a transaction trying to swap token I to the token J, then we add a directly the edge. From I to J, then we could obtain a directed graph like this one. And recall that our strategy space contains two parts: how to select user transaction and how to insert a attacking transaction. Then our first combinatorial structure is about how should we select the user transaction. And we claim that there is an optimal attack that the select user transaction should be acyclic. Okay, I will skip the first sketch here. And the second result is about how should we insert attacking transactions. Actually, actually our results show that it's sufficient to it's enough to just insert the attacking transaction along the existing edge in the undirected graph. So it means that suppose we select these 4 blue transactions, and in the attack you want to insert an attacking transaction from B to C, then I would say it's equivalent to just replace this transaction with a path of transactions along the existing transaction in this graph. And by doing this, you will receive the simulated. Okay, here's our first result about the Fisher market. In the Fisher market, there is a special token, the special centralized token, and all transactions is trying to swap between this special token with all other tokens. So it looks like the graph looks like a star. And in this setting, I think the most crucial lemma is sufficient to just independently attack each pair. And if we look closer at each sub-market, then you can find that there may exist multiple transactions in each direction. But with more effort, we can develop a polynomial algorithm to find the optimal strategy. But I will skip here. But if you are interested, I'm happy to chat about this later. Okay, for the general market structure, the most important insight, I think, is in the general market, instead of locally maximize your utility, instead of locally try to find the optimal price, maybe what really matters is to select as many user transactions as possible. But still remember that the user transaction will be acyclic. That is, we need to select user transactions as many as possible while preserving is still acyclic. And it because of this insight, we just and then we can reduce the feedback offset problem to this MEV optimization problem. And the construction is also inspired by the previous insight. Okay, to summary, I think in this talk discussed the optimal MEV in batch auctions, and we have and we show the point time algorithm for the Fisher market and MP harness for our LDR market. And although our analysis is based on the market equivalent formulation, but I want to convey a general message that for the general batch auction design, MEV is possible, because you may realize the power to manipulate the batch content is enough to manipulate this the results, and this may bring some MEV to the attacker. And as I mentioned, our people also discussed ultimate MEV in the CFM setting. Previous work has shown a point time algorithm for the setting when there's no fee, and our work further discussed the setting with fee, and we show that the problem becomes hard. And for the future work, I think a natural question for the is to study the approximation algorithm for the general market, and further knowing that it may be possible in the batch auction, how to mitigate this problem is very urgent. I think maybe a natural solution is to adopt the commit and review scheme, right? We let the mediator to blindly collect some connections in the batch and make some commitment. Then we review this batch and do the computation. However, I think a drawback of this design is we must need at least one more consensus round, which will cause some latency. Yeah, so more studies on this in this one will be very interesting. Yeah, I will stop here. Thank you very much.
Thank you so much. And as is tradition for this, exactly one question, and you better make it quite snappy. And if nobody has a question, there's a timeout. Okay, cool. I was about to start counting down.
So you mentioned that this is NP hard, and like if I'm assuming this is Ethereum, so every block gets created like every 12 seconds, right? Do you think like given compute rates today, this is possible to do every 12 seconds, given how compute intensive this is?
You mean this algebra marking?
Yeah.
Or the NP hard results?
Yeah, to do it in like 12 seconds within the block.
I would say so. It's the only harness is for the general algebra market. But maybe it can be there could be very many special cases. For example, there only exists some cycle or some special structure may make this problem. I mean, you may find the optimal strategy for some special cases. Yeah, but for the general setting, this problem is still hard.
Awesome. Thank you so much.